2 minutes ago, NASA published a result from the James Webb Space Telescope that made planetary scientists stop mid-sentence. It was not a new planet. It was not a distant galaxy. It was our own solar system. Right here, 8 planets from the Sun, a world we have known about since 1846. Neptune. A planet so distant that it receives 900 times less solar energy than Earth, so cold that the concepts of weather seem to break down, and so mysterious that it continues to defy every prediction we make about how planetary atmospheres should behave. And what James Webb found in Neptune's atmosphere, published in Nature Astronomy in March 2025, was something scientists had searched for 30 years and could not find. When they finally found it, the lead researcher said, "The detail and clarity of the signature really shocked me." Scientists do not say they are shocked by things they expected. They say that when reality does not match the model. And right now on a planet we have studied since 1846, the models are not matching reality. The temperature is going the wrong direction. The auroras are in the wrong place. Something is happening in the atmosphere that breaks the rules we thought we understood. And every time we send a more powerful instrument toward this planet, we discover that what we thought we knew was incomplete in ways that matter. The deepest mystery Voyager revealed was the energy question. Neptune is 4.5 billion kilometers from the Sun, receiving approximately 900 times less solar energy than Earth does. The temperatures at the cloud tops are around minus 220 degrees Celsius, among the coldest in the solar system. And yet, this planet is generating supersonic winds that require enormous energy to sustain. Where does that energy come from? The Sun cannot be providing it. The distances are too great. When instruments measured how much energy Neptune radiates into space compared to what it receives, the answer was astonishing. Neptune radiates approximately 2.6 times more energy than it receives from the Sun. The planet is generating heat from within, a thermal machine running on internal power billions of miles from the Sun. The source of that internal heat and its mechanism remained unexplained when Voyager left the system in 1989. And they remained unexplained for over 30 years. Because, for 30 years, no instrument powerful enough to probe Neptune's atmosphere in serious detail existed. Ground-based telescopes lacked the sensitivity. Hubble could observe Neptune, but lacked the infrared precision needed. The planet held its secrets, waiting for an instrument powerful enough to finally see what lay hidden there. The first Webb image of Neptune, released in September 2022, was about the rings. Voyager 2 had confirmed Neptune has rings, but they were dim and difficult to photograph. No telescope had shown them with real clarity. Webb's first Neptune image changed that instantly. The rings appeared as crisp, bright arcs, showing internal structure never resolved before. The faint dust bands linking the outer rings to the atmosphere, theorized but never directly observed, became visible in the Webb image. Because Webb observes in infrared, the planet itself looked nothing like its familiar blue color. It appeared as a darkened sphere surrounded by luminous halos of ring material glowing in reflected infrared light. The methane in Neptune's atmosphere absorbs infrared efficiently, making the planet itself dim while everything around it glows. Observations made in June 2023 using Webb's near-infrared spectrograph would yield results far more profound. The spectrograph breaks light into component wavelengths and measures precisely what is there, producing a chemical fingerprint. The team, led by Henrik Mellon of Northumbria University and including scientists from NASA's Goddard Space Flight Center and the University of Leicester, pointed this spectrograph at Neptune's ionosphere, the electrically charged upper layer where auroras form when energetic particles from the Sun interact with the planet's magnetic field. The results were published in the prestigious journal Nature Astronomy on March 26, 2025, and immediately began circulating through the astronomical community, shocking researchers and inspiring a cascade of new questions about this mysterious planet. Here is why those results matter so profoundly. Every other large planet in the outer solar system, the great gas giants Jupiter and Saturn, and the ice giant Uranus, has been known for decades to produce auroras. Auroras visible, detectable, observable through a specific and reliable molecular signature. When energetic particles from the solar wind slam into the hydrogen-rich atmospheres of these gas giants and ice giants with tremendous force, they create a molecule called the trihydrogen cation, a molecule with 3 hydrogen atoms carrying a positive electrical charge. Chemical symbol H3+. This molecule, this combination of 3 hydrogen atoms bound together with an extra electron stripped away, glows at specific infrared wavelengths. It emits light in a way that is distinctive, recognizable, unmistakable to the instruments that astronomers use. For decades, this molecule has been used as a reliable marker of auroral activity on Jupiter and Saturn and Uranus. Since the 1990s, when the technology to detect infrared emissions became available, H3+ has been the signature signal. When you see that emission line, you know auroras are occurring. You know the magnetosphere and atmosphere are interacting. You know the solar wind is reaching down to create light in the upper atmosphere. For Neptune, the molecule was expected to be present for the same physical reasons that it appears on every other giant planet. Neptune has hydrogen in its thick atmosphere, primarily hydrogen and helium. Neptune has a magnetic field, an invisible shield generated somehow within its interior. Neptune gets hit by the solar wind, the constant stream of charged particles flowing outward from the sun. All the conditions that produce H3+ on the other planets, every single physical requirement, was present at Neptune. The theory predicted it. The physics demanded it. Every reason to expect the molecule was there, but every time scientists looked for it, using ground-based telescopes in Hawaii and on mountaintops elsewhere around Earth over more than 30 years of concerted effort, they could not find it. Year after year, observation after observation. The molecule that should have been there was simply not there. It was as if Neptune had somehow evaded the physical laws that govern the other planets. The lead researcher on the Webb team described the discovery that changed this 30-year drought in direct, unguarded terms. Looking through Webb's data, sifting through the infrared spectra returned by the instrument, and finding that H3+ mission line was stunning. His exact word, stunning. Not because the molecule was unexpected in theory, not because it violated any laws of physics to find it. It was stunning because the signal was so much clearer and so much stronger than anyone had anticipated after 30 years of failed detection attempts. 30 years of disappointment had conditioned the scientific community to expect that Neptune simply did not produce detectable H3+, for reasons no one understood. But Webb found it in abundance. And because what the infrared spectrograph returned alongside the molecular discovery was an image of the auroras themselves, visible as bright, cyan-colored splotches appearing in Neptune's upper atmosphere like paint splattered across a canvas. Neptune has auroras. They had been suspected through purely theoretical reasoning. They had been predicted by models. They had been searched for unsuccessfully for 3 decades. Webb found them in one observation. In a single-pointed observation at Neptune's ionosphere, the most powerful telescope humanity has ever built, revealed phenomena that had been hidden from humanity since the beginning of recorded civilization. And when the team examined where those auroras were located, where those glowing cyan splotches appeared on Neptune's face, the location added another profound layer of strangeness to an already deeply strange planet. The pattern made no sense in the context of everything we thought we knew about planetary magnetism. On Earth, auroras appear near the poles. The magnetic North Pole and the magnetic South Pole are situated close to where Earth's geographic north and south poles are located, where the planet's rotation axis intersects the surface. Energetic particles from the solar wind follow the invisible lines of force emanating from Earth's magnetic field. These particles spiral inward, guided by the magnetic field, like beads sliding down invisible threads. The field lines converge toward the poles, and that is where the particles meet the atmosphere with tremendous force. That is where the collisions occur. That is where the atmosphere glows. That is where the auroras appear, producing the northern lights and southern lights that are familiar from photographs taken in places like Alaska and Scandinavia and the southern regions of Earth. On Jupiter and Saturn, the same pattern holds. The auroras appear near the magnetic poles. The physics works the same way across different planets. Energetic particles, magnetic field, collision, light. The pattern is consistent. Neptune does not work this way. Neptune breaks the pattern. Neptune's magnetic field is tilted approximately 47 degrees away from its rotational axis. 47 degrees. That is a severe tilt, a dramatic departure from the nearly aligned fields of Earth and the other giant planets. More strikingly, more mysteriously, the center of Neptune's magnetic field is not at the center of the planet. It is offset by a significant distance from the planet's core, sitting off-center in a manner that has no clear equivalent among the other planets in our solar system. The magnetic field of Neptune does not emanate from its center like the field of a bar magnet centered at Earth's core. It emanates from a displaced position, creating a profoundly asymmetrical geometry. The result of this bizarre magnetic geometry is that Neptune's magnetic poles are nowhere near its geographic poles. They are positioned at mid-latitudes, closer to Neptune's equator than to the top or bottom of the planet. They sit at strange angles, at latitudes where you would expect relative calm in the magnetosphere. And because auroras invariably follow the magnetic poles, because they form wherever the magnetic field lines converge, Neptune's auroras appear at mid-latitudes too. They appear scattered across the planet's face in places where you would never expect them if you assumed Neptune behaved like Earth or like Jupiter or like Saturn. They appear in patterns that defy the intuition built from centuries of studying how auroras work on Earth and decades of studying them on other planets. The Webb observation confirmed this directly for the first time with undeniable clarity. Neptune's auroras are not arranged at the poles as every theory predicted they should be. They are scattered across the planet like scattered lights in a city viewed from far away, determined entirely by a magnetic field that is both tilted and off-center. a magnetic compass so broken from the normal planetary pattern that it seems to belong to a different category of object entirely. The planet's magnetic geometry is broken, and its auroras reflect that fundamental brokenness perfectly. They appear where the magnetic field says they should appear, not where simple planetary physics would predict. The magnetic field anomaly may be fundamentally connected to the interior conditions of Neptune, to the hidden depths beneath the methane clouds, to structures and processes that no telescope can observe directly. The standard model of planetary magnetic fields, the theory that has successfully explained magnetism on Earth and other worlds, requires a conducting fluid rotating in the planet's interior to generate the field through what physicists call a dynamo effect. It is like a natural electrical generator running at planetary scale. Earth's magnetic field comes from the rotation of liquid iron in its outer core, spinning and circulating beneath our feet, creating the invisible shield that protects our planet from the solar wind. Jupiter's and Saturn's come from metallic hydrogen deep in their interiors, hydrogen compressed to such tremendous densities that it takes on metallic properties and conducts electricity like a metal. Neptune's magnetic field, tilted 47 degrees from the rotation axis and offset significantly from the planet's center, does not match the geometry expected from the simple dynamo models that work for Earth and the gas giants. It is as if the theory that successfully predicted the magnetic fields of 4 other planets suddenly stops working here at the 8th planet. Some researchers, exploring the possibilities, have proposed that the magnetic field is generated not deep in the planetary core where the theory predicts it should be, but in a thin shell of conducting fluid at an intermediate depth, somewhere between the surface and the core. This shell dynamo model would naturally produce an off-center tilted field, rather than the pole-aligned field that a core dynamo would generate. The asymmetry would be built into the geometry. The offset would emerge naturally from the physics. The liquid diamond hypothesis adds yet another layer to this mystery, another possible piece of the puzzle. Scientists have theorized, based on models of planetary interiors, that within Neptune's depths, at pressures and temperatures exceeding anything we can create in laboratories on Earth, carbon-based compounds could exist in a crystalline form. Liquid diamond. Vast oceans of it, potentially. If liquid diamond exists in sufficient quantities within Neptune, it could theoretically affect the electrical conductivity of the mantle layer, change how electricity flows through the planet's interior, and contribute to the unusual magnetic geometry we observe. An ocean of liquid diamond flowing in Neptune's interior may be tilting the planet's compass in ways we do not yet understand. It is a hypothesis based on solid physics, but it remains unconfirmed, awaiting more data, more observations, more understanding. Neptune, with all its mysteries still unsolved and its basic properties still not fully understood, is about to become, for the first time in the entire history of human space exploration, a priority target for a dedicated spacecraft mission. Not a casual flyby, not a spacecraft passing through the system on the way to somewhere else. A dedicated mission designed specifically to study Neptune, to solve these mysteries, to transform this distant planet from a place of speculation into a place of knowledge. The current planetary science roadmap, driven by the National Academies of Sciences, Engineering, and Medicine's Planetary Science and Astrobiology Decadal Survey, an official assessment by the leading scientific bodies in the United States of what the highest priorities should be for the next 10 years, identified a mission to the Uranus and Neptune system as among the highest priorities for the next decade. Neptune ranks with the search for life on the moons of Jupiter and Saturn as one of the most important destinations for planetary science. The problem is trajectory. To reach Neptune within a reasonable mission timeline within years rather than decades, a spacecraft cannot travel there directly. The distances are too vast. The fuel requirements would be impossible. Instead, a spacecraft needs to use Jupiter's gravity to slingshot itself across the outer solar system. The spacecraft approaches Jupiter, swings around the planet, and uses the planet's gravity to redirect its path and add velocity, like a ball thrown against a wall and bouncing back faster. This gravitational assist maneuver is one of the most elegant solutions in orbital mechanics, and it is essential for reaching the outer planets efficiently. The problem is that the orbital alignment that makes this maneuver possible only occurs every few years. The positions of Jupiter and Neptune in their orbits around the Sun must be properly aligned. The next favorable window for a Neptune-targeted mission is approaching within the late 2020s to early 2030s, a launch window of only a few years. If a spacecraft is not launched by approximately 2030, if the mission does not lift off from Earth in the next 4 or 5 years, the next opportunity is decades away. We are talking about a decision window of less than 5 years to commit to a mission whose arrival is still 15 years in the future. As of 2025 and 2026, mission planning is active. Engineers and scientists are working to design the spacecraft that will carry this mission. Instrument concepts are being developed, ideas refined into actual technologies. And the scientific case for such a mission, powerfully reinforced by every Webb discovery about what we do not understand about Neptune, about the energy paradox and the magnetic anomaly and the temperature mystery has never been stronger. The discoveries of 2023 and 2025 have created an undeniable urgency. But here's what we currently face in the summer of 2025. The James Webb Space Telescope, the most powerful astronomical observatory humanity has ever built, a telescope that cost $10 billion and took 30 years to develop and launch, has looked at Neptune and found auroras that should be there according to basic planetary physics, but were impossible to detect for 30 years despite dedicated efforts by the world's best scientists. It has found them in the wrong place, appearing at mid-latitudes instead of where the theory said they should appear, at the poles, because the magnetic field is broken in a way we cannot explain from the outside, in a way that contradicts our models of how planetary magnetism works. It has found a temperature record that goes in the wrong direction during summer and spikes violently at the pole in ways no model predicted, in ways that suggest the physics of ionospheres is incomplete at ice giants. It has revealed rings that are brighter and more structured and more complex than anyone knew before, rings that showed internal structure that telescopes had never resolved. It has detected a molecule, H3+, that took 3 decades to find and found it in abundance, suggesting something fundamental about the upper atmosphere is different from every previous model's prediction. Every new instrument, every new generation of technology, from Voyager in 1989 to Hubble in the years since to Webb in 2022 and 2023 and 2025, has found that Neptune's previous model was wrong in ways that matter. The models were incomplete. The understanding was insufficient. Reality diverged from prediction. And the planet, 4.5 billion kilometers away, generating its own heat from some unknown internal source, raining diamonds in the dark according to the latest theories about planetary interiors, running its weather on internal power at supersonic speeds in the wrong direction, with auroras at mid-latitude and temperatures that move opposite to the sun's input, is still out there. Still waiting. Still largely unexplored by humanity, still breaking the rules that we thought were universal, still returning mysteries with every observation. And the next spacecraft, capable of answering the deepest questions about what is happening inside this world, about the magnetic field and the energy source and the atmospheric mysteries, if it launches on schedule around 2030, will not arrive until the mid-2040s, 15 to 20 years away. Until then, Webb keeps looking. And every time it does, whenever Webb points its instruments toward this distant ice giant, whenever the data streams back to Earth, the answer it sends back is always the same one. Neptune is stranger than we thought, and we thought it was already the strangest world in the solar system. There is one detail from the 2025 Webb discovery that almost every popular article covering it buried in the middle, relegated to a secondary position, treated as a curiosity rather than a fundamental finding, and it is absolutely the detail that should have been the headline. It is the detail that matters most. When the Webb team measured the temperature of Neptune's ionosphere, when they used the infrared spectrograph to determine how hot the upper atmosphere actually was, they were working from predictions and expectations made by models that had been built and refined over decades, sometimes over many decades. These models are not simple. They take everything we know about how upper atmospheres work in theory, how solar energy from distant stars deposits into ionospheres and heats them, how auroral energy flows and what effects it produces, how gas molecules at extreme cold behave under extreme conditions, and they synthesize all of this into mathematical predictions. The models had numbers. The Webb spectrograph returned different numbers. The measurements came back colder than predicted, not by a small margin that could be explained away by measurement error or minor uncertainties. The mismatch was significant enough that the team stated it directly in their official paper. They wrote it in a way that scientists write when they want to highlight something important. The ionosphere is colder than current models account for. That single sentence means the models are missing something. Some process is removing energy from Neptune's ionosphere, stripping away heat that should be there according to theory, or preventing energy from entering the ionosphere that the current theory of how ice giant ionospheres work does not include in its calculations. And what that process is has not been identified. No one knows. It remains a mystery. This matters beyond Neptune specifically. There are thousands of planets, several thousand confirmed planets orbiting other stars that are approximately the size of Neptune. These distant ice giants appear to be, based on data from the Kepler Space Telescope and the TS mission, among the most common types of planets in the galaxy. They outnumber Earth-like planets. They are ubiquitous. When astronomers and astrobiologists model the atmospheres of those distant worlds, when they try to understand whether they could support life, what their weather systems are like, how they interact with their host stars, whether they might be habitable, they use the same physical principles and the same models that they apply to Neptune. They assume that the physics they understand at Neptune is universal, applicable everywhere. If those principles are incomplete at Neptune, if the models we use to describe Neptune are fundamentally flawed in ways we do not yet understand, then they may be incomplete at every ice giant in the galaxy. Every model built for exoplanet atmospheres may be incomplete. Every prediction about distant ice giant planets may be wrong in systematic ways. Understanding what we are missing at Neptune is not just about understanding the eighth planet in our solar system, not just about solving the mystery of one distant world. It is about building accurate models of the most common class of planets we can currently observe. It is about understanding the majority of the planets humanity knows about. Neptune, the world at the edge of our solar system that we have been studying for nearly 2 centuries, since Urbain Le Verrier predicted its existence and Johann Galle confirmed it through the telescope in 1846, is still teaching us that our physics is unfinished, still returning data that the models do not fully explain. Still, every time a better instrument looks at it, every time a more powerful telescope turns its attention toward this distant world, revealing a layer of reality that the previous generation of instruments missed entirely. The blue sphere that Voyager 2 photographed in 1989 as it made its historic flyby, the pale blue dot that has been the iconic image of Neptune for more than 35 years, the image that many people still think of when they imagine Neptune as a distant, cold, quiet world, is neither quiet nor understood. It is a supersonic thermal engine making diamonds in the dark with broken magnetic geometry and impossible temperature behavior, a world that challenges our understanding of planetary physics at every level. And the scientists studying it in 2025, analyzing the Webb data, puzzling over the mysteries, are saying exactly what scientists said when Voyager first flew past this distant world in 1989. We are more surprised than we expected to be. We expected surprises. We knew Neptune would hold mysteries, but we are more surprised than even those expectations. And that is the most honest and the most important thing any scientist can say about the universe, that reality exceeds expectations, that the cosmos is stranger and more wonderful than we imagined. Triton, Neptune's largest moon, today orbits closer to Neptune with every passing year. Triton is not a native moon of Neptune. It was captured, stolen from its original orbit around the Sun, drawn into Neptune's gravity well, and trapped billions of years ago. Neptune's gravity is slowly, relentlessly stealing orbital energy from this captured moon, causing it to spiral inward on a time scale of billions of years of gradual descent. Eventually, in approximately 3.5 billion years, if nothing changes, Triton will cross what physicists call the Roche limit, the distance at which the tidal forces of a planet exceed the gravitational self-cohesion of a moon, the point at which the planet's gravity is so strong and varies so dramatically from one side of the moon to the other that the moon can no longer hold itself together. When Triton crosses that line, when it descends to that fatal distance, the planet's gravity will be pulling the near side of the moon harder than the far side, straining it, tearing at it, and the moon will simply tear itself apart. It will be ripped to pieces. The debris from Triton's disintegration will spread along its orbit around Neptune and form a ring system, a new collection of rings around this already ringed world. Scientists have modeled what those future rings would look like, used computer simulations to predict their appearance and composition, and the conclusion is striking. They would be substantially more massive and brighter than Saturn's current rings. Neptune, a planet that today has relatively thin, dark rings, will in billions of years have the most spectacular ring system in the solar system, the most brilliant rings, the most massive rings, built from the destruction and disintegration of a moon that was stolen from the Kuiper Belt billions of years before that theft. Neptune collects and destroys. It captures wandering bodies and, over billions of years, tears them apart. It is a world of cosmic violence on geological timescales. And Triton, which is currently so cold that its surface nitrogen freezes into pink ice, which harbors cryovolcanoes that spray liquid nitrogen plumes 5 miles high into its thin atmosphere, glows brighter than Neptune itself in Webb's infrared images. It shines brighter than the planet it orbits, brighter than Neptune in the infrared, precisely because its frozen surface reflects 70% of the light and infrared radiation that hits it. Triton is the most reflective object in Neptune's entire system, the most reflective world orbiting Neptune, and it is the one counting down to its own destruction, slowly spiraling inward, shining brighter and brighter as it approaches its doom. That detail, the captured wanderer that burns brighter than its captor while slowly falling toward it, is what Neptune is when you understand it fully. It is a world defined by energy from the inside, by heat generated from unknown sources in its depths, defined by chaos from the past, by the violent capture of a moon billions of years ago that set the stage for billions of years of future destruction, defined by physics that keeps returning results the models did not predict, results that surprise and puzzle and push us to rethink what we thought we knew. James Webb is the instrument finally powerful enough to start reading what those results actually say, to gather data so detailed that it reveals the true nature of this world. And what those results say, consistently, observation after observation, data point after data point, year after year, is that Neptune is not finished surprising us. Neptune is not finished revealing mysteries. Neptune is a world that will continue to challenge our understanding and push the boundaries of planetary science for as long as we continue to look at it.